In this video presentation, we are going to look at just some common chemistry and what are called feedback mechanisms. These are themes that will be seen throughout the anatomy course, no matter what anatomy course you take. And so this is just an introduction to make sure you understand the difference between some things, and again, these things that we call feedback mechanisms. Now, the first thing I always like to talk about are what I call the 3 I's: isotopes, isomers, and ions. It's really important to make sure that you understand the difference between these, because throughout the anatomy course, you will see these words pop up over and over and over and over and over again. Now, when you're in chemistry or physical science or even earth science and biology, you probably talked about atoms. And so, like hydrogen, helium, you think of those as elements. Well, atoms and elements are kind of go hand in hand. When we talk about an atom is the smallest particle on Earth that has a certain characteristic. And again, one of my favorite things to talk about is structure determines function. And so I constantly use the example of Legos. And so different colored Legos would represent different colored particles. And you know that with atoms have protons, which are positively charged particles that you find in the nucleus. They have neutrons, which are neutral particles that are found in the nucleus, and then you have electrons, which are negatively charged particles that are flying around the outside of the nucleus. Well, that's like having 3 different Legos. If you think of electrons as being electric blue Legos, you think of neutrons as being neutral brown Legos, and you think of protons as being purple Legos. Structure determines function. The 3 parts that you have are going to determine the job that it has. So when we look at an atom, we talk about how, like, if you only have 1 proton, 1 neutron, and 1 electron, that's only 3 Legos to work with. You're not going to have a real complex structure. Well, that's hydrogen. But when I get to helium with 2 protons, 2 electrons, and 2 neutrons, now I have 6 Legos that I can work with. So it's going to be a little bit more complex. So I can build something different. Remember, structure determines function. So when we look at elements are atoms. But what makes each element different are the number of Legos that they have that we use to build them. So when we talk about an element, think of that element as having an address. We talk about how elements are found on the periodic table. And so, for example, hydrogen is number 1, helium is number 2, oxygen is number number 8. I'm getting myself mixed up. Carbon is number 6, nitrogen is number 7. So think of those as house addresses. So every element has an address on the periodic table. And this is based on how many protons it has. So helium is in the number 1 spot. That means it has 1 proton. Excuse me, hydrogen. Helium is at the number 2 spot. It has 2 protons. Well, this is what we call the atomic number. So when you look at the periodic table, think of that as the address. That lets you know how many protons you have. Well, the number of protons usually matches the number of neutrons. And so if you look at a periodic table, you'll see 2 numbers. One number is smaller than the other, but the larger number is almost double what the smaller number is. Well, that represents what we call the atomic mass. That's the number of neutrons and protons added together. So remember, structure determines function. When we talk about the atomic number, that is how many protons it has. And so that gives it its address on the periodic table. When we look at atomic mass, we're looking at protons plus neutrons. Now, a lot of cases, the number of electrons also equal, but electrons are a lot smaller and their mass is different than protons and neutrons. So a lot of times when we do the atomic mass, we're just looking at the protons and neutrons. The electrons are there, that's why there's usually a point something, 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 something. But it's not always equal. So when we talk about isotopes, by definition, isotopes are atoms with different number of neutrons. So for example, carbon. Carbon's address on the periodic table is 6. That means carbon has 6 protons. If it didn't have 6 protons, it wouldn't be carbon. If it had 5 protons, it'd be boron. If it had 7 protons, it would be nitrogen. What makes carbon is the fact it has 6 protons in it. Well, what we consider normal carbon would have 6 protons and 6 neutrons. And so this is what's called carbon-12. And as you can see here, 99% of all carbon on Earth is what we call normal carbon. Well, an isotope has different numbers of neutrons, and they tend to have more neutrons than normal. And when we talk about carbon-13, it's still carbon, so it still has 6 protons. If it didn't have 6 protons, we couldn't call it carbon. But it has 7 neutrons. 6 plus 7 is 13. Carbon-14 is an isotope. It's still carbon. It still has 6 protons, but it has 8 neutrons. Well, carbon-13 and carbon-14 feel a little out of place. They feel a little different. And just like when people are in school, some people feel a little bit different than others, and it makes them uncomfortable. Well, we all know that being different is really cool. You know, we would all hate to be the same. But if you ever felt different, it makes you uncomfortable, and a lot of times you probably wish that you were like the others. Well, you can kind of think of isotopes as being the same way. They're still carbon, so they still have those 6 protons, but these extra neutrons give them some different properties. And they're uncomfortable doing that. So isotopes will try to get rid of those extra neutrons. You can think of them as trying to become something else. Well, this can cause some isotopes to decay. When we say something decays, it falls apart. And when things fall apart, that's what we mean when we say they're radioactive. Because when things fall apart, you break bonds, and when you break bonds, you release energy. So we're going to spend a lot of time in anatomy talking about different types of isotopes and how their radioactivity gives them certain properties inside of our bodies. For example, we all have carbon-14 in our bones. It's a very natural type of isotope. And we know enough about carbon-14 that we know how long it takes a piece of carbon-14 to turn into normal carbon-12, how long it takes for it to break down. Well, we can use that to figure out how old bones are. But isotopes, again, these are atoms that have a different number of neutrons. So this is all still carbon. It all has 6 protons. It's the protons that determines the element. If it didn't have 6 protons, it wouldn't be carbon anymore. But because those neutrons, they have different structures, they're going to have a little bit of a different function. So when we talk about things being radioactive, these things are isotopes. And they're trying to change to either gain extra protons, but they tend to try to get rid of extra neutrons. So speaking of, we also talk about these things called ions. An ion is an atom or a molecule with a net electric charge due to the fact it either has lost or gained an electron. And we're going to talk about how most atoms are neutral, which kind of means everything's equal. Protons equal the number of neutrons, which equal the number of electrons. Well, this isn't a chemistry class, so we're not going to get into valence electrons and how many electrons are flying around in this shell and how many electrons are flying around in that shell. Because honestly, it's been a long time for me. But we do talk about ions throughout anatomy because they play an important role in how cells work. And some of the most important ions we're going to look at are sodium, calcium, and potassium. Like sodium is Na+, calcium is Ca2+, and the potassium is K+. Well, these are all ions you've heard of. And for example, you know that you've always heard that it takes calcium to make strong bones. What a lot of people don't realize is the muscles, your muscles actually need calcium to work. And so your bones store that calcium, and then the bones release that calcium into your bloodstream in order to, you can think of it as feeding your muscles. Sodium and potassium are both needed in order for your body to make electricity. So without sodium and potassium, your nerves, your brains can't create electrical currents like they need to. But because they do have charges, you know that like charges repel and opposite charges draw each other to each other. So you're going to see that our cells have to work in a special manner because ions cannot move around by themselves. And we'll talk more about that later. Okay. So as we go through the course, you'll see why the charge in the atom plays a huge role in how the body works. We're also going to talk about these things called isomers. Isomers are molecules with the same chemical formula, but different arrangements. So for example, I have here butane and I have here isobutane. Well, if you'll notice, they both have 4 carbons and they both have 10 hydrogens. So they have the same chemical formula, C4H10. But it's just like me giving you a bag of electrons, excuse me, a bag of Legos with 6 cherry red, or let me see here, with 4 cherry red Legos and 10 hot pink Legos. Well, if I gave all of my students a bag of Legos with the same number of Legos in them, you're not all going to build the same thing. You're going to make different structures from that. Well, nature only has so many ingredients. So nature has learned that it can take the same ingredients and just build things differently. So like I said, if I gave you 4 cherry red Legos and 10 hot pink Legos, one person might just build a block, while another person might build a little chair with it, or another person might, stack it differently to make a little house with it. So this is what isomers are. Isomers have the same ingredients, they're just built differently. And that's because structure determines function. So it's kind of like a bike. It has 2 wheels. It has, the bike frame, it's got the handles, but somebody could put it together very differently. It's still got the same parts, it's got the same pieces, but if I put it together differently, it's going to work differently. So you're going to see several isomers throughout. For example, one of the most common ones is sugar, C6H12O6. That's what most of you know. And most of you know that as glucose. Well, it's also fructose, it's also galactose. So they all have the same ingredients, they're just put together differently. So again, as we go through this course, we'll be talking about different types of isomers throughout as well. And another major theme you're going to see is homeostasis. The root word homeo is referring to a balance. And homeostasis is this idea that as humans, we need to maintain a constant internal environment. So for example, classic example, you know that our normal body temperature is around 98.6 degrees. Well, so our body sometimes will heat up a little bit, but then it turns off and cools down a little bit. So on average, our body stays at 98.6 degrees. That would be homeostasis. That's the temperature our body needs to stay at. Well, our blood, for example, needs to stay at about the same pH. It's about 7.14. So sometimes it's a little bit higher, sometimes it's a little bit lower, but your body will do certain reactions, which we call metabolism, to make sure that our pH stays at about the same. Salinity, we need salt. Without salts, our nerves will not work. Too much salt can dry out our bloodstream. Not enough salt, our nerves aren't going to work like they're supposed to. So we have to maintain kind of a very constant amount of salt, for example, in our bloodstream. And the same thing with water. Too much water can actually cause cells to explode, but if we don't have enough water, it can cause our cells to dehydrate. So our body is constantly having to do things in order to make sure that we're pretty much the same all the time. We need the same body temperature. We need the same amount of salt in our bloodstream. We need the same amount of fluids in our cells. And this is this idea that we call homeostasis. And so what our body has to do to help with that are things that we call feedback mechanisms. And when we talk about feedback mechanisms, you're going to see we have what's called a positive and we have a negative. Positive does not mean it's good and negative does not mean it's bad. Obviously, we don't want to do what's bad things. But your thermostat is an example of a feedback mechanism. It turns off and on in order to keep your house a constant temperature. So that would be an example of homeostasis. Now, like I mentioned with negative feedback versus positive feedback, these are chemical reactions that your body does in order to help maintain homeostasis. Again, negative feedback does not mean something bad is happening. Positive feedback does not mean that something's good is happening. It's actually kind of, in a weird way, the opposite. 99% of the time, your body is doing what's called a negative feedback system. About 1% of the time, when your body is under what it calls times of stress or being distressed, that's when positive feedback mechanisms come in. But both of these mechanisms use hormones. Hormones are part of what we call your endocrine system. And hormones are chemicals that cells use to talk to each other. It's just like you picking up your phone and calling your friend. every friend has a different phone number. Different cells respond to different hormones. So for example, when my pancreas wants to talk to my liver, it secretes a hormone called insulin. When my kidneys want to talk to my red blood cells, or to my bone marrow to make red blood cells, they'll secrete a hormone called erythropoietin. So hormones are how cells talk to each other. And a lot of hormones have partners. And most hormones in our body are part of what we call a negative feedback mechanism. Like I mentioned, 99% of the time, your body is doing negative feedback mechanisms. And what happens in a negative feedback mechanism is one hormone will turn something on and another hormone will turn something off. Just like your thermostat. If it's hot outside, you want your house to be, let's say, 75 degrees. You set your thermostat at 75 degrees. When the inside of your house gets too hot, the air conditioner turns on. But when the inside of your house reaches the optimal temperature, the air conditioner turns off. Your body does the same thing in a negative feedback. One hormone will turn something on, and when you reach the desired effect, another hormone will turn it off. That gives your body a chance to take a break. And again, 99% of the time, your body is doing negative feedback. So this is the example of keeping our body temperatures the same. If your body temperature gets too high, you begin to sweat. Well, once you cool off, you stop sweating. Or if your body temperature gets too cold, you begin to shiver. Shivering is your muscles' way of giving off heat. And then when your body temperature rises again, you stop shivering. So with negative feedback, something turns on and something else turns off. Now, in the case of negative feedbacks, classic example is the interaction between the liver and the pancreas. Your liver has lots of jobs, and one of its main jobs is to feed your blood. Your blood is alive. Your blood needs to eat, and your blood eats sugar. We have to be real careful with how much sugar we put into our blood. Think honey. Honey is really thick, and it takes a long time to move. Well, if we put too much sugar in our blood can get really thick, and it's not going to flow like it's supposed to. And so that can cause your heart to have to work harder, and it can, cause other problems to happen. Well, your liver needs to be told, like a faucet, when to turn on and when to turn off. And that's one of the jobs of your pancreas. And this is a classic example of a negative feedback mechanism. Now, your pancreas makes two types of hormones. You'll see one hormone called glucagon and the hormone we're all familiar with, which is called insulin. Now, a lot of people know that diabetes has something to do with insulin, but a lot of people don't realize how these two things work. Well, like I said, think of your liver as a faucet. Your faucet does not turn on and off by itself, or at least it shouldn't. Something has to turn the faucet on, and something has to turn the faucet off. Well, one of the jobs of your pancreas is to turn the faucet on. So your liver has a sugar inside of it. This sugar is needed to feed the blood. So what actually happens is blood is constantly going, through your body, and when the pancreas realizes, okay, there's not enough sugar in the blood, it needs to tell the liver to turn on. It needs to tell the liver to release sugar. So it's going to use this hormone here called glucagon. The root word gluc always lets you know it has something to do with sugar. So I think of it this way. Glucagon means glucose be gone. It's telling the liver to spit out sugar. It's telling the liver to spit out glucose, or what's called glycogen, in order to feed the blood. So the pancreas will then send glucagon to the liver, and the liver turns on. So it's like turning the faucet on. And now sugar is going to go into our blood so that our blood can eat. Well, we don't want our sugar to get too thick. You can think of it that way. So when our blood has the sugar that it needs and we don't want a lot of fat to start to build up, our pancreas needs to turn the faucet off. So our pancreas secretes the hormone insulin. Think of insulin as keeping the sugar in. Glucagon says glucose be gone. It's telling the liver to spit out sugar. So you're turning the faucet on. Insulin is telling your liver to turn the faucet off, keep the sugar in. So here in this negative feedback mechanism, one hormone turns something on for a little while, and the other hormone turns something off for a little while. 98% of the hormones in your body work in a negative feedback. So as we go through hormones in the anatomy course, a lot of times we'll talk about partnerships. If a hormone has a partner, one hormone is going to turn something on and the other hormone is going to turn something off. That's going to be a negative feedback mechanism. Now, again, like I said, blood sugar levels are a classic example of this, but it's not the only example. But as we go through the year, we will talk about more of these examples. Positive feedback mechanisms tend to only use one hormone. And positive feedback mechanisms tend to occur when the body realizes something is damaged or something isn't working right. So these don't happen that often, or at least they shouldn't happen that often, because again, these tend to help fix something. So another classic example is when you cut yourself. Well, hopefully you don't cut your blood vessels all the time, so positive feedback should not be happening all the time. Well, when you cut, as you can see in this picture, when you cut a blood vessel, you begin to secrete something called histamine. You've all heard of histamine before when we talk about allergies, but think of histamine as the 911 call. When you need help, you pick up the phone, you dial 911. Well, when your cells are damaged, they secrete histamine. That's their way of shouting for help. Well, when histamine levels reach a high enough amount, platelets will turn on. Platelets are the cells that we use to form blood clots. Well, the platelets will start to make certain hormones, and those hormones cause blood clots to form. And a scab as a blood clot is just on the surface of your skin. The only time you should be making blood clots is when platelets are turned on. And so we don't make blood clots all the time. We don't have busted blood vessels all the time. And so positive feedback mechanisms aren't used that often. They're used to repair things. They're used in times of stress or when something's not working like it's supposed to. They're not that common. So the positive feedback mechanism, it tends to only use one hormone. And that hormone has to be triggered. Something has happened and that hormone is initiated. But once it has finished its job, it turns itself off. It does not need two hormones. So once the blood clot has formed, we know, okay, we're finished here. We have a positive feedback mechanism. Another classic example is childbirth. Okay? Your uterus, ladies, is made from smooth muscle. And by definition, smooth muscle tends to pulse. An exception to the rule is our uterus. Our body has to tell the uterus when to pulse, and it does so using a hormone. And that hormone is called oxytocin, as you can see here. This hormone is also called the labor hormone. So when a female is pregnant, the fetus sits inside of the uterus. And the bottom of the uterus down here is called the cervix. And the cervix is a circular opening, and it's open about a millimeter or 5-6 millimeters on normal. Well, as the child gets bigger, gravity starts to pull the child down. So the cervix starts to open. That's what we mean when we say a female is dilated. Her cervix is starting to open. Well, the body realizes, okay, this is not normal. It's not normal for the cervix to be stretched out this much. So the cervix is sending information to the brain that says, hey, I'm stretching. And the brain says, okay. And the brain starts secreting this hormone called oxytocin. Well, oxytocin tells the uterus to start to squeeze shut. When the uterus starts to squeeze shut, it pushes the baby down. So the cervix opens even more. So the cervix is talking to the brain even faster. So the brain secretes more oxytocin. The cervix opens more. More information to the brain, more oxytocin. So you can see here how it's more. And now the cervix is dilated and the female is open enough that the female can begin to push and the child can come out. Well, as soon as the child is gone, pressure is gone. So the cervix can slowly start to shrink back down to normal. Well, once the pressure is gone, the cervix says, hey, brain, thanks a lot for your help. And so we stop secreting oxytocin. One hormone, positive feedback mechanism.